front a little bit in order to be more interactive with the speakers. There's plenty of room in the front if you want to. You're not obliged to. Okay, let me welcome you to the session on impact. We have two sessions on impact this afternoon, and we look at impact in a broad sense. Societal impact in general, economic impact in more particular some cases, but also the scientific impact. A lot of the work that's been done up so far has probably more scientific impact directly than it has economic impact directly, and only at the longer time frame, time horizon, these other impacts will come. In my thinking, simple, scientific, economic, societal. That's probably the order in where the impact will sort of roll out. We will see examples of the scientific impact, we will see examples of the economic impact, or the possible economic impact is maybe a better way of saying it. And I would like to start off by asking Simon Hodson. Simon is the director of CODATA, and he will take the floor by explaining what they did in the World Fair project. Simon.
Thank you very much, Carol. Good afternoon, everyone. So I'm Simon Hodson, Executive Director of CODATA. I was also coordinator of the World Fair project, and I was the chair of the expert advisory group for that produced the Turning Fair into Reality report, and I was also the co-chair of the expert advisory group that produced the UNESCO recommendation on open science. So that's the sort of coordinatory activity that I do. So I'm going to talk about the scientific and societal impact of the World Fair project. To do that, I'll have to introduce World Fair as well. Input on these slides also from Alexandra Delipalta from RDA Europe, who led the work package on communications and impact and sustainability for the World Fair project. So a little bit about the World Fair project. Subtitle, Global Cooperation on Fair Data Policy and Practice. Now, what was fascinating and wonderful to work on the World Fair project, it was genuinely global. It came not out of the infra-EOSC strand of funding, but from the WIDERA strand of funding, widening the European research area. And we were able to have, because of that, beneficiaries from institutions all around the world, including Brazil, Kenya, Australia, New Zealand, etc., etc. And so we leveraged both the CODATA networks and the RDA networks to find these colleagues. And I should say as well that it built on work that CODATA had been doing since 2018, and which had as its premise that the urgent, major global challenges that we face are fundamentally interdisciplinary. We need to identify solutions through science and through the implementation of science for challenges such as climate change and climate change adaptation, the growth of cities, the loss of biodiversity. All of these challenges do not rely on the science from a single discipline. They need input from our understanding of the natural processes, the human interaction with those natural processes, and the input from the social sciences. So they're fundamentally interdisciplinary. And so our challenge, if you like, for EOSC as CODATA, as a global organization, and as World Fair is, okay, yes, let's build these research infrastructures for particular disciplines, but let's make sure also that they support the science we need, which is fundamentally interdisciplinary. And I'm going to do something that speakers don't often do, but there are two people in the second row here who are chatting away, and it's very distracting, I'm sure for me and for the other people. So may I invite you to either hold your conversation elsewhere or to... Thank you. So, what we tried to do in World Fair was to address this recommendation from the Turning Fair into Reality report. Recommendation 4, which I always felt was the keystone of what we were trying to do. And the most important recommendation there. Develop interoperability frameworks. So that recommendation, I think, has had a significant impact on the thinking in EOSC. We're talking about the EOSC interoperability framework and trying to understand what that means. There's a definition there and in that report. And it says that we need to define practices for data sharing, data formats, metadata standards, all those things that lead to, that support interoperability. But also, again, with this idea of interdisciplinarity. To support interdisciplinary research, the interoperability frameworks should be articulated in common ways and adopt global standards where relevant. We can't do this in a vacuum. We need to try and communicate across disciplines and, yes, adopt global standards that go across disciplines. And this is something that we really try to do in World Fair. World Fair was a 2-year project with a budget of $2 million. I would say this, wouldn't I? But I think we achieved an awful lot. It completed 4 months ago, and I'm going to try and talk about the impact of that in a very short space of time. So to start off, we had a ridiculously ambitious number of case studies. This diagram, when we prepared the project plan, then became our logo. 11 case studies from a range of research areas. 3 relating to chemistry and material science, 3 relating to health and social science, 2 different aspects of biodiversity, 1 involving GBIF, 1 involving pollination in biodiversity, ocean sciences, disaster risk reduction, and cultural heritage. And we didn't just do a surface level, oh, what do these people do? We did a deep dive into the research involved and the metadata standards that they use and the semantics that they use. And at the heart of this is what we call engagement synthesis and recommendations, a work package led by CoData to try and understand those data and how we can present conclusions and recommendations for interdisciplinary interoperability. So that was the plan, and I think we largely delivered on that. There was a methodology which I'm not going to go into a great deal of detail on this, but it's worth mentioning the high-level features. We used FIPS, Fair Implementation Profiles, to understand what people were doing in their particular domains and those case studies. So that was really useful for an insight into that. We then ran a series of intensive workshops with each case study, what we call cross-domain interoperability framework workshops. They were online, but we also used the Darkstuhl venue for 2 week-long intensive workshops at which all the work packages had, on one year or the other, an opportunity to attend. So we leveraged a lot of additional support in that way. We used an advisory group and a working group for the cross-domain interoperability framework, drawn from standards initiatives all around the world. And again, that leveraged a huge amount of voluntary effort for the project. And the outcome was a whole load of reports and recommendations from each of those case studies, so 11 times 2 or 3, depending on the case study, and the CDIF. Right, so now I'm going to move on, and in the last 5 minutes or so, I'm going to rattle through the last few slides on the impact. You've heard what World Fair set out to do. This is a diagram of the impact. I'm not going to go through these in particular order, but I'll try and do these as quickly as possible. So policy and EOSC. So this slide really shows how we responded to the STRIA. Engaged in detail with research communities. And certainly that's something that, from our perspective on the world, from our philosophy, we would recommend to others. So all those outputs for each of those domains. And they're already, many of them are already being implemented. The cross-domain interoperability framework, which I'll say a little bit more about tomorrow, also enhances and adds detail to the EOSC interoperability framework on metadata standards, on semantics, on data structure, on data integration, on how you use what we call universals to join data sets. Please have a look at it. There's a lot of work that went into it, and I think it adds very useful detail to the EOSC interoperability framework. And it's a practical guide. You can take it and start implementing the first 5 modules. And it has a principle, which is adopt widely used standards. We're not inventing new standards. We're not writing new standards. What we're saying is this is how they can be used together. So on the left of the screen there, you can see the first 5 modules and what they address: discoverability, access controls, controlled vocabularies, data description, for integration and universals, for data combination. So that's what CDIF covers, and there are other modules coming. So that's the first step. And this is some feedback we got over the summer from someone who's reading it and who will implement it in a European research infrastructure. And when you've put a huge amount of work into something and you get feedback like that, I mean, I can try and communicate to you, we were absolutely thrilled because they downloaded the report, and we've had over 2,000 downloads so far. They started reading it. They thought, this is way too long. It's over 150 pages. What on earth am I going to do with this? But then they realized that most of that, the space was taken up with implementation guides and directly addressed at that sort of user. Someone in a cross-domain repository in a research infrastructure wants to be able to implement the metadata for cross-domain use. And so I'm not saying the report is perfect, I'm not saying the profiles are perfect, but we've made a very important step in the right direction. We also produced policy recommendations. Now, I can't say that these have had impact yet. We've had some very positive feedback on them, but I think this is an ongoing discussion. But there's a very clear message. We need a shift from a bibliographic approach to metadata to an engineering approach to metadata. And what we mean by that is we're still doing too much. Here's a data package, upload it to a repository, give it a high-level description using an extended version of Dublin Core or something very similar, and that's it. And we hope that the people can download it, work through the README files, figure out what it all is. That is precisely what the PwC report was getting at when they said that we have an opportunity cost without fair data, and 80% of research effort is going into data preparation and wrangling. We need to do better. Not for all data, all of the time, but remember the message about the interdisciplinary research? We needed to do it for those areas of interdisciplinary research. And we think CDIF is a step towards that. So we hope that will have an impact. Now I'm going to have to go through the last few very quickly. Innovation and adoption. And the remainder of the slides, I hope you'll have a look at them, look at the examples, but these are largely examples from each of those work packages, each of those case studies. So as well as the CDIF, as well as that synthesis work, and the policy recommendations, we also have specific recommendations from each of those case studies. So, IUPAC led the International Union of Pure and Applied Chemistry, who look after the periodic table and chemistry nomenclature, changed their practice, adopted things as a result of the project, and made those changes. Immediate adoption and innovation. Likewise, with GBIF, the project contributed to the development of the new GBIF data model. It wasn't the only contribution. In the project, they worked on a part of it to do with camera trap data, but it's immediately adopted because those organizations have international authority for the research areas and the data standards that they look afterwards. Likewise, bidirectional learning on the use of schema.org with JSON-LD, used in ODIS, the Ocean Data Information System, using in SOSA, which is scienceonschema.org, used in the INSPIRE project, which was a member of the consortium, etc., etc. I'm going to have to rattle through these ones quickly, but where are we going now? So we're continuing the World Fair activities. It would be wonderful if we had a new World Fair 2 project, but pending that, we have World Fair Plus, which is a consortium of funded projects. So we have 5 new projects which have been funded by various sources, some by the EC, some by other funders, which are implementing the cross-domain interoperability framework in those areas of research: population health, disaster risk reduction, X-ray absorption spectroscopy data, geology data, climate adaptation, etc. And we're still inviting applications for the CDIF working group and advisory group. If you follow that link, you can see what that's all about. Knowledge transfer, capacity building, lots of training outputs from each of those work packages. In social surveys, which was a collaboration between the Australian Social Survey and the European Social Survey. In chemistry, how to apply those digitized, fair recommendations that IUPAC developed, and in population health, how to implement the recommendations that we were making in that INSPIRE project in Kenya and other parts of East Africa. Environmental, direct impact from all of those case studies in nanosafety, in biodiversity, the new data models I mentioned, agricultural biodiversity. They tweaked the plant-pollinated data model, or developed a plant-pollinated data model in coordination with GLOBI, which is the Global Biotic Interactions Standards Making Authority. And that, again, has already been adopted and is being used and is filling a gap in the IPBES report. And likewise, we had a very good collaboration with the Ocean Science Data Module and the Ocean Data Information System, which is an initiative of UNESCO. And those recommendations, which were developed in consortium as a result of the World Fair project, again, are already being implemented. Social health, social surveys, population health, urban health, cultural heritage, all made outputs which are being implemented. And please follow the links to find out more. And that's it. Thank you very much.
Thank you, Simon, for this almost impossible task in 10 minutes, 15 minutes, to explain about the outcomes of this very impressive project. We move on to another speaker with impact, especially in the domain of ultimately the economics. He will talk about the interaction or co-option, if you want to, of FAIR and AI. Erik Schulzes is the lead of FAIR implementation. He is the expert on verification in the Go FAIR Foundation in the Netherlands. So you can find the rest of his bibliography on the website linked to the Indigo program. Erik, may I invite you?
Great, thank you, Carl, and thank you to the program committee for the invitation to speak. It's an honor. And maybe just to hedge the bet here, Carl was worried that my slides might be a little bit too complicated. So let me preface everything by just saying, indeed, the key issue that I wanted to talk about today was this relationship between emerging AI systems and the role of FAIR as we've understood it over the last 10 years. The punchline is going to be that, in my opinion, FAIR is the flip side of AI. They go together. The economic implication is that there's a huge amount of money moving into AI right now. There will be, I'm sure, societal and scientific impacts, but we can at least stick to the economic issue at the moment. So first slide? Oh, I have that. Yeah, I'm in control. Awesome. Okay. Yeah, so the title of the talk is Fair Data and Data That Are Fully AI Ready. So you see already the acronyms kind of being repurposed in an entirely new way. It works perfectly, right? So I want to give this argument now sort of a little bit of historical context And then a couple small experiments I've run with ChatGPT-4 to kind of make the point, and then I'll try and make the conclusion. So the historical context is, and Simon even alluded to some of this history, this acronym FAIR, as in findable, accessible, interoperable, reusable, was invented in a Lorentz workshop in the Netherlands in 2014. Somehow, 10 years have passed by. We commemorated that 10-year anniversary this January with another Lorentz conference workshop. And you can see on day 4, we're actually talking about fully AI-ready data. Simon and Carl were at that event, by the way. In 2016, this paper was published that enunciated the FAIR principles as we know them today. The PowerPoint's messing up the highlighting. What I wanted to show here was that the FAIR principles were defined back in 2016 as being able to enhance the ability of machines to do F, A, I, and R on their own. So the fact that we use this word enhance the ability of machines, then I'm really sort of holding on tight to that now as we go through the AI storms. In that paper was box 2 with the FAIR principles. After 10 years of working with them, I consolidate the FAIR principles down to this. It's about machine actionability, or I'd say computability. So FAIR data use knowledge representation languages and controlled vocabularies to get rid of ambiguity in human language. And you can actually then express human knowledge in a code-like fashion. It's trustworthiness. So FAIR data have rich provenance metadata that tell you where the data are coming from. So if there's any problems with the data, you can try and infer that from this rich metadata. And then there's this equitability thing, that FAIR data makes explicit the conditions under which data can be reused. So I think these 15 one-liners boil down to these three ideas. So over the course of a decade, lots of interesting FAIR implementations have emerged. I'm showing a view very much biased from my own point of view in the work I've done for GoFair, but there's training, there's practices, there's orchestration platforms that try to really implement F, A, I, and R. There's this very interesting new idea of FAIR data visiting, where data stay put and algorithms come and knock on the door and get access, even to data that are not open. So even confidential data, for example, could become part of the research environment. And then came the LLMs in 2023, and emphasis on large language models. So ChatGPT-4 has almost 2 trillion parameters operating. It costs $100 million to make this model. Those are huge numbers, and it's only foretelling where the industry wants to take this further. So there's a huge amount of money and investment and resources, and by the way, environmental footprints being devoted to these large models. So given that I have this capability now for free on the web, I can talk to ChatGPT. I fed ChatGPT this query, which Mark Wilkinson, the lead author of the FAIR paper, had always used early on, like back in 2017, as an example of what you could do in a world of FAIR data. So he's saying, FAIR search engine, please find me all known low molecular weight inhibitors of the human P65 protein. Separate that list that you find based on curated databases and those that are found in uncurated archives. Keep track of the citation information because I want to be able to reuse this stuff afterwards. If this information is behind a paywall or a firewall, let me know what I need to do to get to it. And what Mark is asking for here is not a pointer to a data repository, not a pointer to a data set. Mark is expecting to get back a list of inhibitors with unique identifiers so that he can put that directly into his workflow and keep going. That was the vision of FAIR back in 2017. When you feed this query into Google dataset search, you're going to get, in Google, you're going to get 500,000 papers to read. In Google dataset search, you're going to get 56 databases, as last time I checked, with an ability to sort on usage. That's nice. When you put it into ChatGPT-4, you end up with a dialogue that comes back where ChatGPT-4 is finding the repositories that are curated repositories, self-deposited archives, and separating out where you can get the reference information. You're still not getting that list of inhibitors, but you believe the model could be trained or helped or supported to do that for you. You can see where this is going. I did another little experiment. This is what we do all the time in GoFairs. We try to assess the fairness of repositories and then figure out how we can improve them. So why not ask ChatGPT-4 to assess its own level of fairness? And I ended up with 25 pages. So I dialogued, we went through each of the FAIR principles. One thing I can say is that ChatGPT-4 understands FAIR much better than most humans. And when you want things to get more technical, if you say, please, can you give me this metadata in JSON-LD? Without hesitation, you get JSON-LD. So we can see that ChatGPT-4 is pretty capable in terms of understanding FAIR and trying to do FAIR. So what does this mean? Can we conclude that AI has now obviated the need for doing FAIR data? Are we done here? And I'm looking at the second to the last bullet point. Do we invest now more in making data fair? Do we need to keep finding projects to do that? Or do we invest more in making machines smarter? Because they can do the work a lot faster than humans can. However, if you ask ChatGPT-4 for its own limitations, and then this is all documented anyways, ChatGPT-4 says, well, we already have human curators involved in the loop, in the training loop. We have to filter out noise, low-quality data, redundancy. We have all kinds of bias and ethical concerns. We don't know how to deal with that. And there's copyright issues. And I think last time I saw on the web, I think there's 10 lawsuits now against OpenAI for copyright infringement and trademark infringement. What I thought was interesting about this list, and I didn't even ask for this, by the way, it was kind of offered to me by ChatGPT. I could map on the FAIR principles exactly to these issues. So the filtering is about computability, getting rid of ambiguity. The trustworthiness aspect of the FAIR principles is about understanding where data come from so you can assess the biases and control for it. And the equitability, of course, is, I have copyrighted material, how can I use this? So here's the conclusion. At the moment, there's a large amount of data out there, a huge amount of data, most of it not fair. But with the training of the AIs, and you can see there's some noise and there's bias issues and there's copyright issues. So just by the sheer volume of data, we can get really good AIs already. But if we were to insert in that process a smaller set of data that was more richly verified, then you could reduce that noise, you get more trust, get more equitability out of the data. And I would assume then that you could get, in fact, better AI, at least liabilities that have, or AI that has lower liabilities associated with it. Those highly trained FAIR AIs could then orchestrate FAIR better, could do FAINR better. They could themselves output in FAIR formats already, so you could begin to assess where this data is coming from, and if you can believe it, from the models. And the AIs could probably more effectively do the verification that's needed at scale that would just be, that might be prohibitive if it's just left up to humans alone. So the last slide here is to say, between 2014 and 2024, this FAIR acronym worked miracles because it connoted this idea of small letters FAIR, or equitable, trusty, reliable. What I see now in the GoFair space is that people are starting to get really excited about making their data AI ready. It's the exact same thing, and even the acronym kind of moves over, right, from FAIR small letters to fully AI ready. But what I could see going forward that has economic impact, and as far as that FAIR is associated with EOSC, would also have economic impact in the EOSC context, is that all the investment going into the large companies for the large language models some commensurate amount of that investment could be spent on the verification of data and building out systems for that. And with that, I would like to say thank you for your attention.
Thank you, Eric. And it's clear it's either the chicken or the egg. We don't know where it started, but it will keep on reproducing, and that's the most important part of it. We have now an online presentation from Giovanni Guerrieri. He's the Data Management Technical Coordinator in CERN and was also the one leading the ESCAPE program. And he's doing the same thing now in conjunction with the Oscars project. I hope it will, yeah, he's there. So Giovanni, can I ask you to start your presentation?
Thank you very much, Karel, and thank you very much to the organizers for having me. I hope you can properly hear me and see my presentation. And in this talk, I would like to go through the societal and economic impact that are coming from CERN and ESCAPE communities, focusing on one of the products of the ESCAPE collaboration, that is the virtual research environment. Now, I'll start with a brief introduction about CERN and ESCAPE. So CERN is a world-renowned international research organization that was founded in 1954, and today, in this year, in 2024, celebrates 70 years of existence. It collaborates with several states all across the world. There are a few member states in Europe, and then there are associate members, observers, and non-member states that are actively contributing to the community. It has been the main actor, let's say, in several groundbreaking advancements, both in science and technology in the last decades. Just to quote a few, the Higgs boson, the World Wide Web, it is currently leading the accelerator and detector technology, let's say, sector, and it also significantly contributes to several open science initiatives. And one of the most popular products, for instance, is Zenodo, that you might be familiar with. On the other hand, the ESCAPE collaboration is a much more recent project that went, let's say, along between 2019 and 2023. It's a consortium including 31 members, and you have a list of them here. And it was funded by the European Union's Horizon 2020 Research and Innovation Program. And just to elaborate a little bit more on the deliverables that actually the ESCAPE collaboration provided, here's a quick, let's say, bullet list with the major achievements that were delivered by the project. I'm not going to go through them, let's say, in a much detail. I will just highlight them in order to somehow provide also a common line to all of them. So we provided a full exabyte scale data management prototype that was adopted and validated through several data challenges by the various stakeholders of the ESCAPE collaboration. We developed a catalog to publish digital scientific products that was somehow, let's say, adopted again by a few of the members of the ESCAPE collaboration, as well as a set of interoperability standards that were mostly aiming for astronomical and data services. Then we developed and we produced a reusable analysis toolkit that somehow aimed to integrate the various services we provide. And in order to prove and to demonstrate this ability, we came up with a virtual research environment as both a prototype and a demonstrator that is being currently leveraged, and let's say several communities are beneficially, let's say, impacted from this initiative. And then we have a few outreach topics, such as the very popular Citizen Science Initiative that really saw a lot of communities really involved in the ESCAPE challenges, for instance. And then a few other demonstrators more in really going specifically on physics topics like dark matter and extreme universe that were really, really appreciated by the community. Now, we see a set of services and results, and I've highlighted the virtual research environment because I believe that this is somehow an aggregator of all these infrastructures and services and resources that we came up with within the ESCAPE collaboration. And just to give a very high-level description of what the VRE is about, the virtual research environment, it serves as an aggregator or a infrastructure and services that are integrated within each experiment or research infrastructure, software and computational resources. We're tackling mostly three main areas, which are the analysis area, the data management area, and possibly an interactive way to somehow integrate both of them, which in this case takes the form of a notebook service. And we take these three topics and we wrap them around an authentication and authorization layer. And what is the end product of this somehow high-level architecture is what you can see on your right-hand side of the slide. So it's a Jupyter Lab, let's say, environment, a very popular Jupyter environment in which we leverage industry standards and we integrate somehow physics related tools such as the data management tool Rusio or the reproducibility and reanalysis tool Reana. And we make this, and what makes this solution actually interesting is that the VRE is modular. Therefore, it's able to integrate heterogeneous software tools and packages within the same platform, and it can, let's say, connect to remote storages and computing resources. Then it is flexible, which is pretty important because several different communities might have different needs in terms of analysis, and people are able to declare in a declarative way to somehow set up their own analysis workflows. And in this case, this is what makes somehow the infrastructure flexible. And then the overall virtual research environment can be installed and deployed on several different machines independently between, let's say, of the CERN requirements that were used during the development. And the last point, which is actually pretty important, is reproducibility. Therefore, the virtual research environment can be used at both a baseline, and let's say a demonstrator for several communities. There are all the tutorials and the resources needed to set up your own virtual research environment. And this makes it reproducible also together with really the capacity of wrapping a whole physics analysis in a preserved environment, let's say. Now, just to somehow get the virtual research environment within a pragmatic context, I would like to showcase just one example, one of the examples that were used within the ESCAPE collaboration to prove the point. And this is a multi-wavelength analysis that involves an astronomical object that is a quasar. Let's say the whole purpose of this analysis is to get several sources, data sources that are scattered around. We have a few sources that provide radio images of the object. We have other sources that provide optical images, and we want to come up with the image that we have on the far right, which is the aggregation, the combination of the two. So we set up our own data lake technology. We are our own, let's say, data lake infrastructure, and within the infrastructure and the VRE, we are able to get data from several different heterogeneous resources, bring them all together, process the images, obtain a result, and upload it back to the data lake. And this brings me somehow, the data management topic, let's say, brings me to a few more use cases that were adopted within the ESCAPE collaboration. Let's say after the project was ended, we had three different, let's say, in collaborations, three different ESCAPE members that actively adopt the data management technology and through the VRE, let's say. And these are the Square Kilometer Array Observatory, the Cubic Kilometer Neutrino Telescope, and the Cherenkov Telescope Array Observatory. And we have currently a few communities that are actively looking into integrating our services, the services provided by the ESCAPE, or let's say produced within the ESCAPE collaboration, leveraging the VRE, which are, for instance, the Einstein's telescope that is currently looking into setting up their own data management system. Now, The next slide somehow explains or tries to explain why are we doing this? Why are we trying to get communities together and develop common tools? So it's a quite dense slide that somehow qualitatively summarizes the efficiency gains and the economies of scale that we can get in scientific computing as a direct result of open science. We get up with common software and computing tools. Having common software and computing tools has two main outcomes. The first one is that we limit the reinvention of the wheel several times to address the same challenge. Therefore, communities are forced, or let's say forced, it's a hard word, but they are fostered communities to communicate together in order to address in a let's say common way, common challenges. And then the other outcome is that we really build a community, a shared community of developers and contributors that are really working towards the same goal, which is very good. Now, the second implication is that we also get shared practices on data analysis based on open data and open science. And this, let's say, brings one main result, that is that we are enabling physicists to do better physics without having to worry too much about setting up the computing resources. And this, to me, is one of the major takeaways that the VRE has achieved within the past years. Then, of course, shared practices on data analysis also imply alignment in coding strategies and hardware approaches, meaning that not only we are, let's say, making strategies and coding more efficient by aggregating ourselves all together, but given that we are forming a community-based initiative, we are also more able to influence hardware design that are typically coming from industry. One example would be that the GPU industry is now really pushing towards architecture that are, let's say, beneficial for LLMs application, artificial intelligence application. But within the scientific computing, we also need GPU architectures that are actually aiming to our own, let's say, kind of operations. Therefore, aggregating together might have a weight in this kind of decision making. And last, we have a very important outreach and, let's say, open science purpose, which is we are really somehow allowing software coding infrastructure to be accessible by not just by experts, but also by general public. Therefore, we are lowering the barrier to entry, and we are allowing a better outreach, a better training, a better open science, but possibly also better open data. So this is a real qualitatively, let's say, takeaway message of what we got or what we think we got from the ESCAPE collaboration. And just to sum up generally the presentation, we believe that we somehow achieved the aim of, and we are achieving and we are continuing, let's say, the aim of getting communities together. This was proved by the various stakeholders from the ESCAPE collaboration that adopted the services we provided. And we also feel we can have a support voice within the more general, for instance, European node. Now, it's not just an outreach initiative, but it also helps the ESCAPE collaboration to build their own momentum, our own momentum within a community-based effort, let's say. So we are actively developing community-based competence centers that are not only acting in an outward way, but they are also looking inside the collaboration to provide expertise, best practices, services, and to really promote cross-disciplinary collaboration. And then this is related to the previous slide, because somehow we see that there are sizable efficiency gains and economies of scale in scientific computing. We are currently working in getting more, let's say, key performance indicators to have a more quantitative analysis of what's happening, but we have a clear vision of what are the benefits that, let's say, working together is implying. And that would be it from my side. Thank you very much.
Giovanni, I hope you got the applause from the audience here, and I would like to ask you to stay online for the panel. Can I invite Eric and Simon up on the stage? And let's see if there are questions in the room before we look at the questions in the slide. Oh, there's at least one because I put it in. Any questions from the room? And let me try to summarize what we've seen. What we've seen is work in the domain of cross-discipline interoperability. So I would say a approach, if I may use that word, Simon, and correct me if I'm wrong, that could also be done in many other situations. We have seen in the case of Eric, the development of AI, fair AI, and the combination of the two and how they will interact and how they can help each other. That may lead to the question, by the way, can we forget about fair for the time being and leave it to the computers? But I don't think so. And the third one is tools that Giovanni showed, where I think the main use has been in the field of astronomy so far, but where you clearly advocate this can be used wider and also should be used in a multidisciplinary approach. Questions from the audience? Yes. There's somebody coming with the mic.
Thank you very much for all the speakers. But I will start with the provocative questions because, well, I was a little surprised that when you show LLMs, you didn't indicate the open models that we can develop as European in this direction. That means we don't need to use the company's LLMs. We can use other models. And I didn't see this in your presentation, because if we want to have an fair AI, we need an open models. And until now, these big companies, the models are closed. And then I want your opinion in this way.
Yeah, sure. So the FAIR principles proper, especially principle A 1.2, talks about authorization and access to your resource. So that was intentional by design, that FAIR was meant to force the data user to be explicit as possible about how their data should be accessed. Whether that's open or closed is up to the user. And so I would say technically, a closed AI model can be perfectly fair because there could be perfectly explicit conditions for getting access to that model or getting inside that model. Now, the question of should it be open is another question, is another story. And I think one thing I would say, just as a warning, these large language models, almost by definition, are a little bit like vendor lock-in happening. Right? These models take a huge amount of resources to create. They're not easy to replicate. They're not practically easy to replicate. So it will be up to it will be up to, I think, the organizations like EOSC to try and set policies on the use and reuse of these models that will be necessarily one-off, one of a kind.
You're doubtful, huh? But fair is different than open. So we would like to have as much open as possible. But there are, of course, developments that cannot be open for good reasons, and they still can be fair. And thus, taking into account all the requirements there. Simon, there's a microphone over there if you want to. No, it's switched on already.
Okay, thanks. Before I add something to that, as I've been grumpy and outspoken already today, I'm going to do it again. I hadn't realized that I was going to be on a panel. I promised a few years ago that I wouldn't do that. Through inattention, I didn't see who the speakers were. And so I will say that we should do better, and we shouldn't have a group of guys on the stage. Now
we take that.
Moving on, but remembering that. Moving on about AI. There was a meeting convened by the International Union of Geological Sciences recently, which I think encapsulates a number of our concerns and aspirations around AI. And we need to think about the benefits, because there clearly are, and the risks, and also a lot of the argumentation, pro and con, and why it's being used. Now, there is an international initiative that's sponsored by the International Union of Geological Sciences called Deep Time Digital Earth. It's a big data platform, and it has a lot of Chinese investment, not exclusively so. And they have developed a thing called GeoGPT, which is being used. Now, the meeting convened by the IUGS was to try and deal with concerns and consternations in the community. We need to pay a lot of attention to this because, yes, as the questioner asked, this is beginning to close down the wish for openness. Weren't 10 or 15 years ago, weren't we arguing that we needed open so that we could do meta-analysis, so that we could do data mining? And now we're concerned that some companies may have the control over those technologies and be using them without reference to science or without the involvement of the scientific community. And yet on the counter, so those concerns may be legitimate, but we also want it open for these reasons. And so we need to figure out what the response to this is. Some of the arguments against the generative AI in the example that I spoke about came from the publishers because the data was being used without their consent. And yet at the same time, Taylor and Francis are changing their T's and C's and selling the data that they have to Microsoft for generative AI. There is a lot of hypocrisy, there is a lot of conflicting positions. We need to unpack that. It's not going to be easy, it's going to be complex. But in terms of what we, EOSC, and people that care about this should do, we need policies, they need to be flexible, they need to adapt to situations, and above all, I do think we need fair, upstream, but we need to drill down further into that and what that actually means. And AI ready, it's a nice slogan, but we need to be more serious about it than that, I think, and really we still need the human in the loop, but we also still need metadata in the loop. So detailed metadata descriptions, initiatives like Croissant, initiatives like DDI, CDI, which add detailed metadata at the variable level, so that we try and constrain what the generative AI can do, and we try to understand better what is coming out of the neural network. Now, that was a lot of points in a short amount of time, but I think that shows what the complexity is. But these are the things that we're trying to address, and we need to unpack them and try and put them back together again.
Question over there. Maybe you can wait until the microphone is there.
You mentioned that the things have to be moved from Dublin core to more general engineer description. So my question is, do you think in the near future there can be limit number, not to small limit number, for all discipline to describe the metadata or the data itself, then the conversion from one discipline to another will be easy and new type of research will come?
Short,
Thanks. Yeah, I'll try and respond to that. So I'm not saying we're moving away from Dublin Core. Dublin Core will still have a role. But we've got to be more ambitious in what we mean by data stewardship. And that's the point. And that's that we're trying to be a little bit polemical, but we're trying to rattle some cages and bang on some walls and try and encourage people to be more ambitious about what data stewardship means in EOSC. Think about the use case. The use case is that you need to combine data from many different sources. There's a very good example that came out of EOSC Future. Very simple, a relatively simple one, but incredibly hard. Environmental data of various sorts, Earth observation, pollution data, air quality data, etc., and European social survey data around attitudes to climate change, pollution, etc. You need to combine them. So you need to think about, we have linkers, which is time and space generally, and we need to be able to move the data around from different formats, okay? Now to do that, you don't, sometimes we sort of think, oh, it's going to be a huge semantic mess and we need 1 million crosswalks between the semantics. Not always, it depends what you're trying to do. But in order to do what I've just described, you need accepted descriptions of time and place, and you need accepted descriptions of the data structure so that you can break the data apart and put it back together in the model that you need. Now, the EOS Future project, Climate Adaptive Cities or whatever it's called, showed how that can be done with detailed metadata at the variable and the datum level. And they showed how you combine variables from different data sets into compound variables. IODOP does a little bit of this, and then you pass that down into the data product, okay? Now, that needs an engineering approach, a more detailed data description. You can't do that with Dublin Core, and what we expect in most research projects is people download that, and they do that activity, but one-off, with a lot of manual intervention. It can't be automated because the metadata has not been standardized. And we're not saying that that research doesn't go on. It goes on all the time.
Simon, this was the short answer. Giovanni, you have a question. There's another question in front. And then we have one question from the Slido, and then we quit. Huh?
So, a number of
you have a number of questions. Oh, okay.
important issues being raised. Very quickly, I think the EOSC is stimulating something good on the data acquisition stage, and that is the development of fair by design technologies. So we want as much the data and the metadata coming from the original research stage, not so much retrofitted by some algorithms. Although that may be helpful in some cases, but the most genuine data and metadata we have from the researchers, the better. That is one point. The other point is that indeed I do believe that the main effective user of the EOSC will be algorithms. This is going to happen anyhow, and the user will have to ask the correct questions, and some level of acceptability of the question must be introduced, and then the machines will go around through the data spaces. But this brings up a point that has been raised. Which algorithms? So the algorithm, we would like to be transparent, to be in the hands of the scientific community, not in some unknown hands. And here, I just urge one thing, that although the discussion of what I personally call hyper-metadata, those that will be guiding the algorithms to find where the information is a very important one. There is also the point of not missing this need of having genuine, transparent, and scientifically oriented algorithms. And I just observed that once more, there is a big activity with the AI factories program of the Commission that mentions innovation, that mentions other things, but does not mention research. And this is a problem, so let's not do this mistake again of going on in independent directions, because science would be the best test for AI, and AI would be the best friend for fair, supported science, if it's not ill-funded, but genuinely funded, or at least well understood by the scientists.
Thank you, Giorgio. I think we stop with this remark. Otherwise, if I continue with other questions. Unfortunately, there's a few interesting questions in the Slido, but you can look at those. And I also will suggest that our speakers look at those. As a last remark, I want to tell you that our next impact session has a full female panel. So we have not been able to get the balance right here. We worked on it, we thought about it, we realized it, but we were not able. And on the other hand, the other panel will be full female. Thank you very much.